Midair knot making with lifting and support aerial robots. Knots are widely used across domains such as sailing, climbing, and transportation, motivating their study in aerial robotics. When converting the original knot into a grid diagram, we want to identify which points require support robots to maintain the knot's topology. Our loop consistency filter addresses this by analyzing the grid representation, detecting loops, determining which must be preserved, and assigning robots to hold those loops open. The output of the loop consistency filter is a compact set of support points sufficient to preserve the knot's topology. With these supports, a suspended cable forms catenary curves that, from above, appear as straight segments. If intermediate robots are removed, intermediate segments will form a straight line that could alter the topology. So we need to make sure two things: relax the cable segments between support robots and preserve the knot's topology. To achieve this, we model the formation as a dynamical system with two forces: a straightening force that relaxes the cable and a spring damper force that preserve the knot topology. Here is a demonstration of the relaxation process for a 3-crossing knot. The method works sequentially, applying a straightening force to each intermediate point between support robots to smooth the spans and preserve the knot's topology. To validate our approach, we implemented a physical testbed with 2 types of aerial robots. A customized Crazy Fly bolt acts as the lifting robot, holding the cable endpoints and maintaining global tension. Smaller Crazy Fly 2.1 quadrators serve as support robots, positioned along the cable to regulate internal spans. Robot motion is tracked in real time with an OptiTrack system and controlled through ROS. We can see the robots forming a 3-crossing knot, also known as an overhand knot. Here, the robots are forming a 4-crossing knot. The cable is held by one lifting robot at each end, and supported at key points by intermediate robots, as determined by the loop consistency filter. With fewer robots than the baseline grid method, the cable naturally relaxes into smooth spans through the action of straightening and spring damper forces. This allows the team to preserve the knot's topology while reducing redundancy, demonstrating efficient midair knot formation. The robots are forming a 5-crossing knot. A key insight at this level of complexity is the appearance of the staircase braid pattern. In the baseline method, every corner would require its own robot. In contrast, our approach treats the entire braid as a single span, stabilized by just one circulating robot. This shows how the framework assigns support only where it is structurally necessary, rather than at every crossing. As a result, even complex knots can be stabilized efficiently, preserving topology while greatly reducing the number of robots required.